Beyond the orbit of Neptune, where sunlight arrives as little more than starlight, something ancient drifts through the emptiness. 3I/Atlas moves with the patience of geological time, its dark surface absorbing the faint radiation of a universe 4 billion years in the making. This wandering comet nucleus, no larger than a small mountain, carries within its frozen structure a library that spans stellar neighbourhoods, though humanity has only recently begun to suspect what stories lie locked in its ice. The object itself appears unremarkable through telescopes, a smudge of darkness against the starfield, notable primarily for its trajectory. Unlike the familiar comets that swing in predictable ellipses around our Sun, 3I/Atlas follows a hyperbolic path that speaks of origins beyond our solar system's gravitational embrace. It approaches from the direction of the constellation Lynx, though its journey began long before that particular arrangement of stars had meaning to any observer. The comet's motion through space resembles that of a stone thrown across a vast lake, touching our solar system's surface only briefly before continuing onward into the deep. Within the comet's nucleus, water ice forms crystal lattices that have remained undisturbed for eons. These structures, more ordered than any earthly library, preserve molecular arrangements that date back to when our Sun was merely one young star among millions in a different galactic neighbourhood. The ice itself tells time through its layers, each microscopic stratum a chapter written in the language of cosmic chemistry. Embedded within these crystalline matrices lie traces of elements forged in stellar cores, scattered by supernovae, and gathered slowly from the interstellar medium during the comet's long voyage between star systems. As 3I/Atlas glides through the outer solar system, it maintains a surface temperature of -230 degrees Celsius. At such cold molecular motion slows to near stillness, creating conditions where even the most delicate chemical signatures can persist unchanged across cosmic distances. The comet becomes, in effect, a natural cryogenic storage system, one that has been collecting and preserving data since before Earth's continents took their current shape. This frozen archive exists in a state of suspended animation, where chemical reactions that would occur rapidly at room temperature might take millennia to complete, if they complete at all. The comet's surface bears the accumulated dust of interstellar space, particles so fine they would be invisible to the naked eye, yet collectively forming a record of every region through which the object has passed. Some of these grains originated in stellar atmospheres billions of years ago, ejected by red giant stars in their final evolutionary stages. Others condensed from the cooling debris of supernovae, carrying within their atomic structure the signatures of stellar nuclear synthesis. Still others formed in the cold molecular clouds where new stars are born, gathering ice mantles and organic compounds in the perpetual darkness between stellar nurseries. Scientists recognize that this frozen archive may contain information about stellar environments that no longer exist. Chemical fingerprints from stars that died before our planet formed. The comet may have encountered stellar winds from massive blue giants that exhausted their nuclear fuel in mere millions of years, their brief but brilliant lives ending in explosions that seeded nearby space with heavy elements. It may have drifted through the extended atmospheres of red supergiants, collecting samples of stellar material directly from sources now collapsed into neutron stars or black holes. Yet the irony persists that as the comet approaches closer to our Sun, the very process that makes it observable also begins to destroy the pristine record it carries. Solar heating causes sublimation, releasing ancient molecules into space where they dissipate like whispered secrets into the void. Each day of sunlight erases portions of the archive, transforming solid history into vapor that streams away in the comet's developing tail. The closer 3I/Atlas approaches to our star, the more rapidly it loses the very information that makes it valuable to science. The comet's trajectory suggests it has travelled perhaps 50,000 years to reach our solar system's edge. Though the ice within its core may preserve much older memories, the mathematics of orbital mechanics indicate that 3I/Atlas originated from the general direction of Vega, that brilliant star that served as the northern pole star when Egyptian pyramids were young. Yet Vega's current position relative to the comet's trajectory suggests the object began its journey when that star occupied a different location in our galaxy's slow rotation, adding layers of complexity to the puzzle of the comet's origin. Only a visitor from such distances could carry undisturbed samples of interstellar space, that vast repository of dust and gas that fills the apparent emptiness between stars. Within that seeming void lie the remnants of stellar explosions, the exhaled atmospheres of dying giants, and the raw materials from which new worlds eventually form. The interstellar medium, though tenuous beyond earthly comprehension, contains enough material to form countless solar systems, given sufficient time and the gravitational nudge of passing molecular clouds. The comet drifts onward through the outer darkness, carrying its cargo of frozen time, indifferent to the telescopes that track its passage and the questions it might answer. In the crystalline depths of its nucleus, ancient starlight remains trapped in chemical bonds, waiting for instruments sensitive enough to read the stories written in isotopic ratios and molecular signatures. For now, 3I/Atlas keeps its secrets, a wandering library whose most profound chapters remain unread, drifting through the space between worlds with the quiet patience of deep time itself. In the regions where 3I/Atlas has wandered, temperatures hover just above absolute zero, creating conditions more stable than any earthly laboratory could maintain. Here, in the deep cold between stellar systems, molecular motion slows to a whisper, and chemical reactions that would complete in milliseconds on Earth might require geological ages to finish. The comet nucleus exists in this realm of perpetual winter, where even helium would freeze solid and nitrogen becomes as brittle as glass. This is a temperature regime so extreme that it transforms the fundamental nature of matter itself, creating states of preservation impossible under any other cosmic circumstances. The physics of extreme cold transforms the comet into something approaching a perfect preservation medium. At negative 270 degrees Celsius, water molecules arrange themselves into crystalline structures that can maintain their precise geometry for billions of years. These ice crystals form with a regularity that rivals the most carefully grown synthetic diamonds, creating matrices capable of trapping and holding individual atoms in fixed positions across cosmic timescales. Within these frozen lattices, the history of interstellar chemistry lies suspended like insects in amber, each molecular arrangement a testament to conditions that existed when distant stars were young. Thermal motion, that fundamental driver of molecular change, becomes negligible in such cold. Atoms that would normally vibrate with enough energy to break chemical bonds instead remain locked in place, their quantum states frozen into configurations that preserve information about the environments where those bonds first formed. The comet becomes a three-dimensional archive where each molecule occupies precisely the position it held when first incorporated into the growing nucleus, creating stratified layers of interstellar memory that record the passage of time in molecular detail. The quantum mechanics of extreme cold create phenomena that exist nowhere else in nature, at temperatures approaching absolute zero. The wave functions of neighbouring atoms begin to overlap in ways that create extended quantum states spanning multiple molecules. These quantum correlations can preserve information about magnetic fields, radiation environments, and chemical conditions across vast stretches of space and time. The comet's interior becomes a natural quantum computer of sorts, storing data in the coherent states of its constituent atoms. The comet's internal structure resembles a vast library written in ice, where different layers record different epochs of its journey through space, near the surface. Relatively recent editions of interstellar dust and gas mark the comet's passage through our galaxy's local stellar neighborhood, an area dominated by the solar winds of young, hot stars and the shock waves from recent supernovae. Deeper within, older layers preserve samples from regions of space that may no longer exist as they once did, their donor stars having evolved beyond recognition or exploded in supernovae that redistributed their mass across light years of surrounding space. Scientists studying similar interstellar objects have discovered that the deep cold of space creates unique chemical conditions impossible to reproduce on Earth. Reactions that would be energetically forbidden at higher temperatures become possible when molecular motion decreases to near stillness. Complex organic molecules can form through quantum tunneling effects, where particles pass through energy barriers that would normally block their interaction. The result is a chemistry of extreme patience, where molecular complexity accumulates grain by grain across millions of years, building structures that could never form in the brief. Energetic environments of planetary surfaces. The preservation capabilities of such cold extend beyond simple chemical stability. Magnetic fields frozen into the comet's structure maintain records of every stellar wind the object has encountered during its interstellar voyage. These fields, trapped within the ice like fossilized lightning, carry information about the magnetic environments of distant stars and the turbulent interactions between stellar atmospheres and the interstellar medium. Each encounter with a stellar magnetic field leaves its signature embedded in the comet's frozen matrix, creating a magnetic memory that spans the comet's entire journey through space. Within the comet's nucleus, isotopic ratios remain locked in the precise proportions they held when first incorporated from interstellar gas clouds. These ratios serve as fingerprints of stellar nuclear synthesis, recording the nuclear processes that occurred within the cores of stars that existed billions of years ago. Some isotopes present in the comet's ice may have formed in the first generation of massive stars, those ancient giants that forged heavy elements when the universe was young and filled space with the raw materials for planets and life. The crystalline structure of the comet's ice creates microscopic chambers where individual gas molecules remain trapped like messages in bottles. These molecular cages preserve samples of interstellar atmospheres, carrying within their atomic arrangements information about the density, composition, and temperature of the regions through which the comet has passed. Some chambers may contain noble gas atoms that have travelled unchanged since their formation in stellar cores, while others hold complex molecules that assembled slowly in the cold chemistry of interstellar space. Yet the mystery remains of how long such perfect preservation can continue. Even at temperatures approaching absolute zero, quantum effects ensure that some molecular motion persists. Over cosmic timescales, this residual energy might gradually alter the stored information, like a message slowly degrading through countless generations of copying. The comet carries within itself the fundamental tension between preservation and decay, between the desire to maintain perfect records and the inexorable tendency toward entropy that governs all physical processes. Radioactive decay within the comet's nucleus provides a constant, gentle source of internal heating that may alter the deepest ice layers over billions of years. Uranium and thorium trapped within dust grains continue their slow atomic transformations, releasing energy at rates measured in individual particles per second. This internal warmth, though barely detectable, may create microscopic temperature gradients that allow limited molecular rearrangement even in the coldest regions of the nucleus. The irony of 3I/Atlas lies in its simultaneous role as preserver and destroyer of information. While the deep cold maintains chemical signatures across interstellar distances, the comet's journey also exposes it to cosmic radiation that gradually alters its molecular structure. High-energy particles from distant stellar explosions strike the nucleus continuously, breaking some chemical bonds while forming others, slowly rewriting portions of the archived data even as other sections remain pristine. This cosmic radiation represents both a threat to the comet's information content and a source of additional data about the high-energy environments it has encountered. The formation of the comet itself represents a gradual accumulation process that occurred over millions of years. Individual molecules and dust grains collected from the interstellar medium gradually built up the nucleus through gravitational attraction and electrostatic forces. This slow accretion process created natural chronological layers within the ice, with the oldest material concentrated toward the nucleus center and newer additions forming the outer layers. The result is a temporal archive where the comet's journey through space can be read like tree rings, each layer recording the conditions that existed when it formed. As the comet drifts through our outer solar system, it encounters the faint but increasing warmth of our Sun. This thermal gradient creates subtle temperature differences across the nucleus, with the sunward side warming by perhaps a few degrees, while the shadowed regions remain locked in their original cold. These microscopic temperature variations begin to activate molecular processes that have remained dormant for millennia, starting a gentle awakening that will eventually compromise the comet's role as a perfect archive. The mathematics of heat transfer through ice predict that significant warming will require months or years to penetrate the comet's interior, but the process has already begun. Solar photons, carrying energy accumulated over 8 minutes of travel from our star's core, begin their patient work of molecular disruption, gradually returning the frozen library to the fluid state from which it originally condensed. The comet's approaching transformation represents both an opportunity for observation and an irreversible loss of information, as ancient molecular arrangements surrender to the entropy of warming. In the deepest cold of its interior, 3I/Atlas maintains conditions that may not exist anywhere else in the solar system. Here, in chambers of ice more isolated than any earthly cave, molecules arranged by processes that occurred when our galaxy was younger wait in perfect stillness. The comet carries forward these samples of ancient space like a time capsule, though one that will inevitably open as solar heating gradually penetrates its frozen heart. Within these innermost regions, the archive of interstellar chemistry remains most perfectly preserved, waiting for instruments sensitive enough to read the stories written in its crystalline structure. Within the crystalline heart of 3I/Atlas, starlight from distant suns lies trapped in forms more permanent than any earthly photograph. Cosmic rays and stellar radiation, those invisible messengers that carry information across interstellar distances, have slowly embedded themselves into the comet's water structure over the course of its 4-billion-year journey. Each photon that struck the comet's surface during its voyage left microscopic traces, altering the arrangement of atoms in ways that preserve information about the stellar environment from which that light originated. The process begins when high-energy radiation encounters the comet's ice, breaking apart water molecules and creating free radicals that quickly recombine into new configurations. These radiation-induced changes occur at the atomic level, creating defects in the crystal lattice that serve as permanent markers of radiation exposure. Different types of stars produce characteristic radiation signatures, and these signatures become encoded in the damaged crystal structure like a form of cosmic braille, readable only by the most sensitive instruments. Ultraviolet light from hot. Young stars creates different patterns of molecular disruption than the infrared radiation from cool red giants. The comet's ice preserves these distinctions with remarkable fidelity, maintaining separate records of each type of stellar encounter within different layers of its frozen matrix. Near the surface, recent radiation damage reflects the comet's passage through regions dominated by the intense ultraviolet output of massive blue stars, while deeper layers preserve the gentler signatures of older, redder stellar populations. X-rays from stellar coronae and the accretion disks around compact objects leave their own distinctive markings in the ice. These high-energy photons penetrate deeper into the comet's structure, creating radiation damage patterns that extend throughout the nucleus. The resulting crystal defects form a three-dimensional map of the high-energy environments the comet has encountered, preserving information about stellar activity cycles, coronal mass ejections, and the violent processes that occur around neutron stars and black holes. The comet's ice acts as a natural dosimeter, accumulating radiation exposure over geological timescales. Scientists studying terrestrial ice cores have found that even relatively brief exposure to cosmic radiation creates detectable changes in crystal structure, changes that persist for thousands of years under earthly conditions. In the much colder environment of interstellar space, such radiation-induced modifications could remain stable for billions of years, creating an archive of stellar radiation that spans the comet's entire journey. Gamma rays from distant supernovae have left their signatures embedded throughout the comet's structure. These most energetic photons in the electromagnetic spectrum can penetrate the entire nucleus, creating cascade reactions that affect thousands of molecules simultaneously. The resulting damage patterns preserve information about stellar explosions that occurred millions of years ago and millions of light-years away, their energy finally coming to rest in the crystalline structure of wandering ice. The wavelength-dependent nature of radiation absorption means that different stellar spectra create distinctive fingerprints in the comet's ice. Stars with different surface temperatures emit light with characteristic spectral distributions, and these differences become permanently encoded in the patterns of radiation damage throughout the nucleus. Hot blue giants produce intense ultraviolet radiation that creates one type of crystal defect, while cool red dwarfs emit primarily in the infrared, producing different patterns of molecular disruption. Yet the mystery lies in determining whether current analytical techniques can distinguish between radiation signatures from different stellar sources. The overlapping effects of billions of years of cosmic ray exposure may have obscured the subtle differences between individual stellar encounters. Each new source of radiation adds its signature to the existing damage patterns, potentially creating a palimpsest where newer information overwrites older records. The comet's rotation during its interstellar journey has created asymmetric patterns of radiation exposure across its surface. Areas that spent more time facing the direction of travel would have encountered higher fluxes of interstellar radiation, while regions that remained in the shadow of the comet's own bulk show different damage patterns. These variations in radiation exposure create a complex three-dimensional map of the comet's orientation and motion throughout its journey. Though deciphering this map requires understanding the comet's rotational history, magnetic fields associated with stellar winds have influenced how charged particles from space interact with the comet's surface. In regions where the interstellar magnetic field was strong, charged cosmic rays would have been deflected away from the comet, creating zones of reduced radiation damage. Conversely, areas where magnetic fields focus charged particles onto the comet's surface show enhanced radiation signatures, The resulting patterns preserve information about the magnetic environments the comet encountered during its interstellar voyage. The energy deposited by cosmic radiation has created microscopic heating effects within the comet's ice, causing localized sublimation and recrystallization on scales invisible to the naked eye. These thermal effects have redistributed some of the original interstellar material, creating chemical gradients that reflect both the original composition of collected gas and dust and the subsequent effects of radiation processing. The result is a complex chemical landscape where radiation-induced changes interweave with the comet's original structure. Some radiation signatures may preserve information about stellar phenomena that are no longer active. Wolf-Rayet stars, those massive objects that shed their outer layers in powerful stellar winds, leave distinctive radiation fingerprints during their brief but spectacular lifetimes. If 3I/Atlas passed near such a star during its active phase, the radiation signature would remain preserved in the comet's ice long after the star itself evolved into a white dwarf or exploded as a supernova. The irony persists that the very process of studying the comet threatens to destroy the radiation record it carries. Telescopic observations require reflecting sunlight from the comet's surface, and that reflected light indicates that solar heating has already begun to alter the outermost layers where the most recent radiation signatures are preserved. Each day of solar exposure erases portions of the radiation archive, transforming solid history into vapor that streams away in the comet's developing tail. As 3I/Atlas continues its approach toward the inner solar system, the increasing solar radiation flux begins to compete with the ancient stellar signatures preserved in its ice. The sun's intense electromagnetic output starts to overwhelm the subtle traces left by distant stars, gradually erasing the delicate patterns that took billions of years to accumulate. The comet's radiation archive faces an ironic fate: destruction by the very type of stellar radiation it has spent eons collecting and preserving. As 3I/Atlas traversed the galactic disk during its billion-year odyssey, it encountered stellar neighborhoods as diverse as any collection of earthly cities, each leaving its own distinctive chemical signature in the comet's accumulating layers. The object's hyperbolic trajectory suggests a complex gravitational history, with multiple close encounters that altered its path and exposed it to the unique atmospheric compositions of different stellar systems. Each passage near a star represented an opportunity for chemical exchange, as stellar winds and planetary atmospheres contributed their molecular signatures to the comet's growing archive. The stellar main sequence presents a spectrum of chemical environments, from the hydrogen-rich atmospheres of young blue giants to the metal-enriched winds of ancient red dwarfs. 3I/Atlas may have drifted through the extended heliospheres of stars across this entire range, collecting samples of stellar wind particles that reflect the nuclear burning processes occurring in their cores. The comet's ice preserves these samples in chronological layers, creating a record of stellar evolution that spans multiple generations of galactic rotation. Young massive stars burn through their nuclear fuel with spectacular intensity, producing stellar winds rich in freshly synthesized heavy elements. If 3I/Atlas passed through the vicinity of such stars during their main sequence lifetimes, its ice would have captured particles containing newly forged carbon, oxygen, and silicon atoms still carrying the isotopic signatures of their stellar birthplace. These elements, incorporated into the comet's structure, preserve information about stellar nuclear synthesis rates and the chemical enrichment of interstellar space by massive stars. Red giant stars present different chemical opportunities, as their expanded atmospheres shed material enriched in the products of helium burning and S-process nuclear synthesis. During their asymptotic giant branch phase, These stars produce copious amounts of carbon and complex molecules in their cool, extended atmospheres. A comet passing through such an environment would collect organic compounds and carbon-rich dust grains that reflect the unique chemistry of stellar senescence, preserving samples of stellar material that would otherwise be dispersed into the interstellar medium. The comet's journey may have included passages through stellar systems containing multiple stars, where complex gravitational interactions create turbulent environments rich in chemical mixing. Binary star systems often produce enhanced stellar activity, including coronal mass ejections and stellar flares that accelerate heavy elements to high velocities. These energetic events could have embedded unusual isotopic ratios deep within the comet's structure, creating chemical fingerprints that reflect the violent dynamics of close stellar pairs. Planetary systems encountered during the comet's journey would have provided opportunities to sample atmospheric gases escaping from distant worlds. Hot Jupiters orbiting close to their parent stars lose atmospheric material through hydrodynamic escape, creating extended clouds of hydrogen, helium, and heavier elements that a passing comet could collect. The chemical composition of these escaping atmospheres reflects both the original planetary formation environment and subsequent atmospheric evolution, potentially preserving information about exoplanetary chemistry in the comet's ice. The galactic chemical gradient means that stellar systems at different distances from the galactic center possess systematically different heavy element abundances. Stars formed in the inner galaxy, where supernovae have enriched the interstellar medium with metals over billions of years, produce stellar winds with higher concentrations of elements heavier than hydrogen and helium. Conversely, stars in the outer galactic disk retain more primordial compositions, with stellar winds dominated by hydrogen and helium. The comet's chemical layers may preserve this galactic gradient, recording its journey through regions of different metallicity. Supernova shock waves create unique chemical environments as they propagate through the interstellar medium, compressing gas clouds and triggering rapid chemical reactions that would not occur under normal conditions. If 3I/Atlas encountered such shock fronts during its journey, the resulting chemical signatures would be preserved in its ice as distinct layers rich in shock-synthesized molecules and isotopically anomalous material. These encounters would have occurred over time scales of centuries to millennia, long enough for significant chemical exchange between the shock-heated gas and the comet's surface. The asymmetric structure of stellar magnetic fields creates preferential directions for stellar wind flow, concentrating certain chemical species in equatorial outflows while others escape preferentially through polar regions. A comet's trajectory relative to a star's magnetic field orientation would determine which chemical components it encounters most strongly. This geometric effect means that even identical stars could leave different chemical fingerprints depending on the comet's approach vector, adding complexity to the interpretation of the preserved chemical record. Wolf-Rayet stars, those massive objects in the final stages of stellar evolution, produce some of the most chemically distinctive stellar winds in the galaxy. These stars have shed their hydrogen-rich outer layers, exposing cores enriched in carbon, oxygen, or nitrogen depending on their evolutionary state. Their powerful stellar winds carry these processed elements into space at velocities exceeding 1,000 kilometers per second. A comet encountering such an environment would collect material with extreme isotopic ratios and unusual chemical compositions that clearly mark the encounter with this rare type of star. The chemical signatures preserved in 3I/Atlas may include isotopic anomalies that point to specific stellar nucleosynthesis processes. The ratio of oxygen-16 to oxygen-18, for example, varies systematically among different types of stars and stellar evolutionary phases. Similarly, The abundance of elements like lithium, beryllium, and boron reflects the cosmic ray bombardment history of the regions through which the comet has passed. These light elements are destroyed in stellar interiors but produced by cosmic ray spallation reactions in interstellar space. Molecular clouds, those stellar nurseries where new stars form from collapsed gas and dust, present another distinct chemical environment that the comet may have encountered. These regions are characterized by complex organic chemistry occurring at extremely low temperatures, producing molecules like methanol, formaldehyde, and polycyclic aromatic hydrocarbons that are rare in the warmer environments around active stars. If portions of the comet's ice formed through accretion in such molecular clouds, they would preserve samples of this cold interstellar chemistry. The temporal evolution of galactic chemistry means that the heavy element content of interstellar gas has increased gradually over cosmic time. Material collected by the comet during the early phases of its journey would reflect the galactic chemical composition of billions of years ago. When fewer generations of supernovae had enriched the interstellar medium with heavy elements, the deepest layers of the comet's ice may preserve samples of this more primordial galactic environment, providing a direct sample of the galaxy's chemical evolution. Yet the challenge remains of distinguishing between chemical signatures from different stellar encounters when they may have occurred millions of years apart and become mixed through slow diffusion processes within the comet's ice. The preservation of distinct chemical layers requires that the comet's interior remained cold enough to prevent significant molecular migration, but even at interstellar temperatures, some chemical mixing occurs over geological timescales. The result may be a complex chemical palimpsest, where the signatures of different stellar encounters have become partially blended. The comet's chemical record faces its greatest threat as it approaches our solar system and begins to warm under increasing solar radiation. The sublimation of surface ice preferentially removes the most volatile compounds, potentially erasing the chemical signatures of the most recent stellar encounters first. This selective loss means that the chemical information most accessible to telescopic observation may be the least representative of the comet's complete journey, as the most ancient and deeply buried chemical signatures remain locked within the nucleus, while surface layers evaporate into space. As 3A/Atlas continues its passage through our solar system, it carries within its frozen heart a library of stellar chemistry that spans the galaxy's recent evolution. Each molecular arrangement preserved in its crystalline structure represents a sample of stellar wind, atmospheric escape, or interstellar chemistry that occurred under conditions no longer accessible to direct observation. The comet serves as a traveling museum of galactic chemical evolution, though one whose exhibits face inevitable destruction as solar heating gradually returns its ancient ice to the cosmic medium from which it originally condensed. The magnetic memory of 3A/Atlas extends beyond simple chemical preservation, encompassing the electromagnetic signatures of every stellar environment the comet has encountered during its interstellar wandering. Magnetic fields frozen within the nucleus preserve information about stellar magnetic activity, solar wind interactions, and the complex electromagnetic landscape of the galaxy itself. These magnetic signatures, trapped in iron-rich dust grains and crystalline defects throughout the ice, create a three-dimensional map of galactic magnetism that spans billions of years of cosmic history. Iron and nickel particles embedded within the comet's structure act as natural magnetic recording media, similar to the magnetic tape used in early computer storage systems, but operating on molecular scales across cosmic timescales. Each grain of metallic dust carries magnetic domains aligned according to the field orientation it experienced when first incorporated into the comet's growing nucleus. These magnetic orientations remain stable in the extreme cold of interstellar space, preserving directional information about magnetic fields that may no longer exist in their original form. The stellar magnetic fields encountered by 3I/Atlas vary dramatically depending on stellar type and evolutionary stage. Young, rapidly rotating stars generate powerful dynamo-magnetic fields that extend far beyond their visible surfaces, creating magnetospheres comparable in size to planetary orbits. Older stars with slower rotation rates maintain weaker but more stable magnetic configurations. The comet's magnetic record preserves evidence of both types of encounters, with strong magnetic signatures marking passages near active young stars and subtler patterns recording interactions with the gentler fields of stellar maturity. Solar wind particles carry not only the chemical signatures of their parent stars, but also magnetic information encoded in their trajectories and energy distributions. Charged particles spiraling along magnetic field lines create characteristic patterns when they impact the comet's surface, embedding directional information about the magnetic field geometry and the resulting radiation damage. These patterns accumulate over time, building up complex magnetic maps that record the three-dimensional structure of stellar magnetospheres encountered during the comet's journey. Binary star systems present particularly complex magnetic environments, where the interaction between two stellar magnetic fields creates dynamic patterns of field reconnection, magnetic loops, and plasma instabilities. A comet passing through such a system would encounter rapidly changing magnetic conditions as the stellar fields interact and reconfigure. The resulting magnetic record preserved in the ice would reflect this temporal complexity, with different layers showing evidence of varying magnetic orientations and strengths corresponding to different phases of the binary system's magnetic cycle. The galactic magnetic field itself leaves its signature throughout the comet's structure, providing a large-scale reference frame against which stellar magnetic encounters can be measured. This galactic field, though weak compared to stellar magnetospheres, maintains relatively stable orientations over the timescales of the comet's journey. Magnetic grains aligned with the galactic field create a background pattern throughout the nucleus, while deviations from this pattern mark regions where stronger stellar fields temporarily overwhelm the galactic magnetic environment. Supernova shockwaves compress and amplify magnetic fields as they propagate through the interstellar medium, creating regions of enhanced magnetism that can persist for thousands of years after the initial explosion. If 3I/Atlas encountered such magnetized shock fronts, the resulting magnetic signatures would appear as distinct layers within the nucleus, characterized by unusually strong and well-ordered magnetic orientations. These supernova magnetic signatures preserve information about stellar explosions that occurred millions of years ago and light-years away. The magnetic record also contains information about cosmic ray interactions, as these high-energy particles follow magnetic field lines and create secondary magnetic effects when they impact the comet's surface. Regions of space with strong magnetic fields tend to deflect cosmic rays, creating zones of reduced radiation damage, while areas with weak fields allow higher cosmic ray fluxes. The correlation between magnetic signatures and radiation damage patterns throughout the comet's structure provides additional information about the electromagnetic environments it has encountered. Planetary magnetic fields encountered during close approaches to stellar systems would leave their own distinctive signatures in the comet's magnetic record. Hot Jupiters with strong intrinsic magnetic fields create extended magnetospheres that could interact with a passing comet, while terrestrial planets with weaker fields might produce more subtle magnetic effects. The magnetic signatures of planetary encounters would be distinguishable from stellar magnetic effects by their smaller scale and different temporal characteristics, as planetary magnetic fields change more rapidly than stellar ones. The temporal evolution of stellar magnetic fields means that the magnetic signatures preserved in different layers of the comet reflect the magnetic activity cycles of encountered stars. Young stars often display highly variable magnetic behavior, with frequent magnetic reversals and complex field geometries that change over periods of years to centuries. Older stars tend toward more stable magnetic configurations with longer cycle periods. The comet's layered magnetic record may preserve evidence of these stellar magnetic cycles, though interpreting this information requires understanding the relationship between the comet's accretion rate and the timescales of stellar magnetic variability. Magnetic reconnection events in stellar coronae and stellar wind interaction regions create impulsive magnetic signatures that appear as sudden changes in field orientation and strength. These events, analogous to terrestrial magnetic storms but occurring on stellar scales, would leave distinctive marks in any material passing through the affected regions. The comet's magnetic record may contain evidence of such events, preserved as abrupt transitions between different magnetic orientations in adjacent layers of the nucleus. The preservation of magnetic information requires that the magnetic carriers within the comet remain below their Curie temperatures, the critical points above which thermal motion overcomes magnetic ordering. For most magnetic minerals, these temperatures are well above the conditions in interstellar space, ensuring that magnetic signatures remain stable throughout the comet's journey. However, as the comet approaches our solar system and begins to warm, some magnetic carriers may approach their Curie temperatures, threatening the integrity of the most thermally sensitive magnetic records. The three-dimensional nature of magnetic field preservation means that the orientation of magnetic carriers throughout the comet's volume contains information about the comet's rotational history during its interstellar journey. If the comet maintained a stable rotation axis, magnetic signatures would show consistent orientations relative to the nucleus structure. Conversely, if the comet's rotation axis precessed, or if it experienced chaotic tumbling, the magnetic record would reflect this rotational complexity through varying orientations of magnetic carriers in different parts of the nucleus. Yet the challenge of reading the comet's magnetic memory lies in separating the signatures of different magnetic encounters from the complex overlapping patterns created by billions of years of magnetic field exposure. Each new magnetic environment adds its signature to the existing magnetic record, potentially overwriting or modifying earlier information. The resulting magnetic palimpsest requires sophisticated analysis to distinguish between primary magnetic signatures and secondary effects caused by later magnetic processing. As 3I/Atlas continues its passage through our solar system, our Sun's magnetic field begins to interact with the ancient magnetic signatures preserved in the comet's structure. The solar magnetic field, though relatively weak compared to the fields of more active stars, gradually penetrates the outer layers of the nucleus as solar heating reduces the magnetic stability of surface materials. This ongoing magnetic interaction represents both an opportunity to study the comet's magnetic properties and a threat to the preservation of its ancient magnetic memory. As solar magnetic effects slowly overwrite the signatures of distant stellar encounters,